Qubits. Qubits are the fundamental building blocks of a quantum computer, similar to how classical bits are for regular computers. However, qubits are far more powerful. Unlike a classical bit that can only be a 0 or a 1, a qubit can exist in a state of superposition, meaning it can be a 0, a 1, or a combination of both simultaneously. Think of it like a spinning coin rather than one that is already landed. Qubits can also be linked together through a property called entanglement. When qubits are entangled, their fates are intertwined, no matter how far apart they are. Measuring the state of one entangled qubit instantly influences the state of the other S. This interconnectedness allows quantum computers to perform many calculations at once. Different physical systems can be used as qubits, such as trapped ions, superconducting circuits, or photons. Quantum Processing Unit, QPU. This is the chip or core physical structure where the qubits are located, housed, and interact with each other. The design of a quantum processor depends heavily on the type of qubits being used. For example, superconducting QPUs have intricate circuits cooled to near absolute zero, while trapped ion QPUs use electromagnetic fields to hold ions in place. The QPU is designed to protect the delicate quantum states of the qubits from external noise and to allow for precise control and measurement. It's where the actual quantum computations, the application of quantum gates to qubits, take place. The quality of the QPU, including the number of qubits and their coherence times, how long they can maintain their quantum state, is a major factor in a quantum computer's power. Control systems. To make qubits perform calculations, we need to precisely control their quantum states. This is done using control systems. For superconducting qubits, these are typically microwave pulse generators. Carefully shaped microwave pulses are sent to individual qubits on the QPU to nudge their quantum states, effectively performing quantum operations or gates, the quantum equivalent of logic gates in classical computers. For other types of qubits, like trapped ions or photonic qubits, precisely tuned lasers are often used for this manipulation. These control systems must be incredibly accurate, as even tiny errors in the pulses can corrupt the quantum computation. The complexity of these control signals increases significantly with the number of qubits. Measurement system. After a quantum computation is complete, we need to read out the result. This is the job of the measurement system. Measuring a qubit forces its superposition to collapse into a definite classical state, either a 0 or a 1. This process is fundamental to quantum mechanics. The measurement system must be able to accurately determine this final state for each qubit involved in the computation without disturbing them prematurely. For superconducting qubits, this often involves sending a weak microwave signal to resonate with the qubit and detecting the phase or amplitude shift of the reflected signal. For other qubit types, techniques like fluorescence detection for trapped ions are used. The result of a quantum algorithm is typically a probability distribution, so the computation and measurement are often repeated many times. Cryogenic system. Many leading types of quantum computers, particularly those using superconducting qubits, require extremely cold operating temperatures, colder than outer space. Just fractions of a degree above absolute zero, 273.15 degrees Celsius or 0 Kelvin. This is achieved using a dilution refrigerator. This elaborate cooling system uses multiple stages to progressively cool the quantum processor down. The extreme cold is necessary to minimize thermal noise and vibrations, which can easily disrupt the delicate quantum states of the qubits and cause decoherence, loss of quantum properties. Maintaining these ultra-low temperatures is a significant engineering challenge and a major part of the infrastructure for these quantum computers. Not all qubit types require such extreme cooling, but many do. Classical control computer and software interface. A quantum computer doesn't operate in isolation. It requires a classical computer to manage its operations. This classical computer is responsible for several tasks. 1. Translating a quantum algorithm, written by a programmer, into the specific sequence of control pulses microwaves, or lasers needed to manipulate the qubits. 2. Sending these instructions to the control hardware. 3. Initiating the measurement process. 4. Receiving the classical data, 0s and 1s, from the measurement system. 5. Processing these results, which might involve statistical analysis if the quantum algorithm was run multiple times. The software interface allows users to program the quantum computer, set up experiments, and retrieve and analyze the output. Quantum error correction systems. Qubits are incredibly fragile and susceptible to errors from environmental noise, imperfections in control signals, and decoherence. These errors can ruin a quantum computation. Quantum error correction is a set of techniques and protocols designed to detect and correct these errors. Unlike classical error correction, where bits are simply copied, QEC is more complex due to the no-cloning theorem. You can't perfectly copy an unknown quantum state. QEC typically involves encoding the information of a single logical qubit across multiple physical qubits. Special syndrome measurements can detect errors without collapsing the primary quantum information of the logical qubit. While fully fault-tolerant QEC is still a major research goal and not a single part you can point to in all systems, the hardware and control systems are designed with QEC protocols in mind, often requiring additional control lines, measurement devices, and sophisticated classical processing to implement these correction schemes.